Thank you and welcome to the presentation on injection molding of plastic optics, particularly new approaches in simulation. So what we are going to see in this talk is the optimization and preparation of a simulation procedure that can in fact resolve tiny features and small components down to micro components. Because with the injection molding and micro injection molding, you can mold, in fact, products with dimensions overall above 1 millimeter, but with features in the micrometer range. You can mold micro parts below the millimeter, so mass in the milligram range. And here you can see an example compared to a human hair. And then also micro precision parts without micro features, but with tolerances in the micrometer range and dimensions around a millimeter. So at the end, what we are going to show is a comprehensive method that can address all these three types of molded and precision molded components. So micro injection molding and its variation is not just a downscaling of conventional injection molding, it's special machinery, specific micro tooling technologies, micro nano metrology, and specific simulation strategies, which is the main topic of the talk and one of our developments in ProSurf. So on one side, we have the molding process. So with a number of techniques and features, such as sensors on machines, sensors on molds, and data analytics, we can build what's called the digital shadow of the molding process. On the other side, we have simulation. So with a number of techniques and specific results, so we can actually build the digital twin of the process with a comprehensive simulation. And what we are going to show, part of the research has been building a solid validation that can confirm how the simulation methods can replicate the process with sufficient accuracy, even when we are dealing with micro parts and precision miniaturized parts. So the background for this is a work that spanned the last probably 10 years, in which we have dealt with 100 milligrams parts and some micro features, miniaturized parts in the range of 10 milligrams, micro parts in the milligram range, and in fact a case below 1 milligram. And we are going to see that the overall the method can be applied across different scales and sizes. When it comes to ProSurf, so the objective to obtain specific product functionality by having a microstructure surface, we have applied simulation to the specific case of this relatively large in terms of dimension product, a microstructure Fresnel lens. A lens that has features in the range between 10 and 350 micrometers, as you see here, and a pitch of 748 micrometers. So in this case, the molded part is 10 grams. So it's technically a molded product, but with a fairly large microstructure area. So the challenge here with multi-scale molding simulations is to embed the product geometry, which you can see here, the microstructured area with a finer and higher resolution mesh, and the objective to replicate or simulate the polymer replication for each feature. So in this configuration, already the element count is of 3.2 million. So what we are showing here is the possibility of having an overall part mesh, a higher density of the microstructure area, and then selected features are meshed with even finer, so a third level mesh resolution. Now, when it comes to simulation validation at part level, we can run what's called short shots molding experiments, and then we can superimpose those experiments with simulations. And one condition to enable high accuracy validation is that we implement actual molding conditions in the boundary conditions of the simulation. One example of this would be the screw position over the injection time, in which you can see the actual displacement of the screw is then perfectly replicated in the simulation. And what you can see is a fairly good agreement between the melt front flow position in a specific time step and what has been achieved during the experiments. This is true at this initial filling stage, just over the middle of the structure area, and then when the part is almost filled until it's complete filling. Now, once we get this type of result, it means that in the time domain, both speed, so the mechanical conditions of the flow, and also its thermal conditions are believed to be fairly well calculated, and that means we can go to the next step, which is the simulation and the validation of filling of the features, which is what you can see here in the ultra-fine region meshed. Now, this is what can be seen in a 3D, and then we can even cut the simulation, so the domain here, and see the polymer filling in the time domain the feature of the lens. Once the simulation has been completed, then we can also look at results. The polymer is actually cooling down, shrinking, and what we can see is the comparison with 3D laser microscopy acquisition on the molded lens with the shape of the polymer in that specific filling stage. In this case, when the injection stroke is 16 millimeter, for example. So this is the first part of the filling, and this is when the complete filling is achieved. So when the injection stroke is in fact 20 millimeters. In the actual molding, we have a slight rounding here, and the actual it's around 20 to 30 microns from the simulated one. So this is the setting up of that multi-scale simulation and a number of results that can be achieved. What I'm going to show you now is how the same method also applies to microparts. Now we are in the milligram mass range. So we're going from a part which is 10 grams to 1 milligram, and that's a scale factor of 10,000. So in this case, we have this micro ring of 2.2 milligrams and a mold which has 4 microcavities. We know that in order to get the best, most accurate results, once again, we have to mold and simulate the part, but also the runners here. One specific problem that should be solved here is the presence and formation of this weld line that could affect the functionality and also avoid any air entrapment here at its junction. The validation here is based on a number of experiments in which we explore, in fact, the overall experimental process window. So a number of combinations in which we have 2 mold temperatures, 2 melt temperatures, different injection speeds and packing pressures. So why is that? Well, we want to check whether now the multi-scale simulation method, in which once again you see a fine, fairly fine mesh in the runner area, and then an ultra-fine mesh in the part area. So elements from 500 microns down to 50 microns can replicate the experimental conditions for all the explored combinations. So here you can see the filling of the runner, the force pro, and the 4 microcavities. Once this is in place, we can even study the formation of the flow front going around that central hole and looking at the presence of maybe air traps here or down here. Now, once the calculation has been done, as discussed for the Fresnel lens, comes the packing phase, but also the cooling that brings shrinkage in the polymer. And that will be the phase that at the end determines the dimensions, which in this case, we want to check whether even the dimensional prediction of this part, as for the micro features, is reflected then in the experiments. What we know from experience now is also that extensive experimentation also comes at a cost, and it's also time consuming. So we would like to prove the fact that with multi-scale simulations and high accuracy simulation, it is actually possible to replicate different process conditions and their outcome on the part. What you can see here is the outer diameter of the ring as it has been obtained in the experiments, and in black the simulation. So there is a slight bias in the single-digit micrometer domain, so in a way lower than the allowed tolerance. And also we can see that overall the main trends, which are the relationship between the process conditions, the overall combinations, and the outer diameter, are in fact correctly calculated. So the average deviation of all these experiments to simulation comparisons is down to 1.6 microns, and with an overall variation that is just within 14 microns. And we should stress that this is on a 4-cavity micromoles, in which the part is actually 2.2 milligrams. Once we reached this result, we wanted to see how far we could go, or this simulation method using the virtual design of experiments as well as the multi-scale modeling can work at yet one order of magnitude lower mass of the part. So here we have this little microcap at 0.1 milligram mass range. So that's the size of the component compared with the human hair. It's a thin wall part with wall thickness within 100 and 200 microns. So with a preliminary mold configuration, we observed that due to the tiny volume of the cavity, the high pressures necessary to mold such a thin wall part, but also due to the high accuracy of the part, the mating surfaces of the mold are also very accurately manufactured. So it's basically hard for the air in this extreme condition to escape. So we will encounter a large air trap in this area. Therefore, the tool has been further engineered with a slight venting area so that the residual air here could be pushed out the outer diameter of the cap. However, in these extreme molding conditions, it's very easy to flash the part, meaning that at high speed, high pressure, and high melt temperature, viscosity is actually pretty low, So the melt could go out the edge, and then we would have a poor quality part that will not meet the quality. So with multi-scale modeling, it is possible to extend the cavity beyond the part wall, and we can build a digital twin of this cavity by including also the venting area. Now that has not been tried before, so we had to run a validation study to prove that this was based on sound assumptions, and especially at this scale. So what you can see here, we have the full runner, sprue in the part, and here the effect of the venting. So the melt is actually going outside the edge. So we will have a complete part, no air traps, but an uncertainty as whether the edge could be well replicated. So the idea here is to find through simulations the exact process combination that will lead the full formation of the edge, but avoiding the flash. The venting area is a 4 microns thick annular channel, so it's very much like a micro feature. The process combination had to be found in a certain process window, and again we are looking at 2 different mold temperatures, 2 different melt temperatures, and then 2 injection speeds and 2 packing pressures. So experiments would lead to, in fact, 16 different sets of microparts in which the flash here is a lower or a higher area, and then the simulation would be accordingly. What we can do is to measure by image processing this area in the experimental part and in simulations. So here we can observe that the virtual DOE experiments by simulations really reflect the same trends that we encounter in the experiments. However, the simulations, of course, they correct the predicted effects, but overestimates the flash area by a factor 2. On the other hand, you could see that we are talking about fractions of square millimeters. So with the overestimation of 2, we could find that combination of process parameters that can lead to a minimized flash. Based on this method, we are continuing our work here. This is a recent developments from this year, 2021, and actually presented this week at the USPEN 2021, in which we have a small microfluidic system with a 50 millimeter long, 100 microns deep channel, in which you can see here the multi-scale modeling has been applied to then simulate how deep and how wide would be the microchannel based on mold dimensions and process combinations. And on the optical parts, we have also looked at this 4 cavity 16 by 16 millimeters QR code, both from experiments and simulations. And here you can see how, once again, on the time domain, the injection pressure with accurate implementation of molding conditions can actually be simulated. So once this validation has been made, we can rely on the calculation of the conditions of the polymer and then explore different process combinations without actually performing experiments. So by doing the virtual experiments. So the takeaways, we have 5 main messages. So the flow of position can be predicted in micro and conventional injection molding, as you have seen, from the large Fresnel lens to the micro parts. Micro feature replication now can be simulated using multi-scale meshing and the solving. Injection pressure, injection time can be validated using short shots, as shown in the talk. We can run simulation down with the micrometer dimensional accuracy, so we can predict dimensions of microproducts and features, and the process behavior can be predicted across different process combinations with the virtual DOE and the digital twin of the molding process. So many thanks to ProSurf, and many thanks to you for your attention.